All right, so I thought I'd help you with the visualization of these magnets coming in towards these loops and then how the current would be produced as a result of that. So keep in mind from what we talked about Friday that current will tend to flow around a loop of wire as it's responding to changes in magnetic field around it. So it's trying to reduce that change. If you think about it like it's always trying to resist the change that's occurring. So in problem number one, what we're visualizing is these field lines brought in towards this loop. And so what it's doing, if you look at the cross-sectional area of the loop, let's say if we look at it head on, when it's way out here, when the magnet's really far out, you might only have, let's say, 3 or 4 field lines going into it. So that's looking from this perspective. Let's say there's about, I don't know, 4 field lines. And as I bring it in closer, okay, and start to pack more of those lines in there, what's happening is the number of field lines that are inside that loop is increasing. So as you bring this magnet in, you're bringing more and more north-facing field lines, or basically field lines that are pointing into the loop viewed from the orientation of this magnet. That's if we're, the picture I have off to the side is if we were looking from the north pole of the magnet straight into that loop as we bring it in. And those field lines would be intensifying. So the current is going to run to counteract that. So it's going to try to send back, think of it like which way would current have to move to send dot lines through that ring. So to cancel out those X's, we need to move charge around the wire in a way that would send dots back through the loop. So the way to think about that is if your current, if you need to send dots, and let's just look at one little section of wire here. If I have wire, or if I have current moving up the wire in that location, practice that curled hand rule. Imagine yourself as just a little straight piece of wire there, and then as you're gripping around that wire, there's going to be, concentric circles. It's hard to draw this, but there's going to be concentric circles, and that would be happening at basically all points around this loop. And so we'd want to keep orienting it so that the B field lines would curl and have dots on the inside of this loop. So we're going to be moving that charge in that way. Now that, to me, is very confusing. We're used to drawing one wire, and if the current's going like this, then we'd have X and dot fields. That's what I'm drawing technically right at that location. And on the inside of the loop, we're getting dot fields to be created if we run current in that way. These dots will start canceling with the X's that I drew before, and so that they're counteracting that increase that's happening. So pretty much the current is running in a way to counteract the increasing X's. You're trying to battle back and increase the dots to maintain what the state was. So I would draw that current in number one as flowing around the wire this way. And that would mean that that position A would be full of positive charge, and position B would be negative charge. If we imagine this bulk flow of charge moving, it creates this constriction point. They have a little resistor here. So you get a buildup of positive charge on this side and a lack of positive charge on the other side. And that's how we draw our induced voltage that was just generated by this change. All right, and number two, you can think about if these field lines were super intense inside, so we had a lot of X's. Again, this is viewed, the picture off to the side here is viewed from the north magnet straight into that loop. So imagine we have a whole bunch of X's, a super concentrated field There'd be a large flux with a value of B times A. And we're going to be changing that flux. So when we change a flux, that's when we have current produced. So by moving this magnet away, you start to see the B field lines get less and less intense inside of there. And if I don't have this expanded all the way out, but if I just kept going, it's like we're losing B field lines as this thing gets drawn away. So the number of B field lines inside that ring is decreasing. So if the X's are decreasing, we're going to move current around that ring in a way to bring back the X's. Remember, it's always trying to reduce change. It's not necessarily always trying to battle X's. The point is that the X's are decreasing. Therefore, we need to reinforce those X's to bring it back up to where it was. We're always trying to reduce the change that's happening. And so to make more X's occur, we're going to have to move current in the exact opposite way we did in the last problem. Whoops, sorry. This last one needs to be the other direction. So there we go. So I want you to imagine again that you are on this. Let's change the look of this. There we go. If you're at this section right here in the loop, okay, and your current is running pretty much vertically at that point, what that's going to look like, we zoom in, you have current going up the wire, and again, practicing your hand rule, that would mean on the inside of the loop, or to the right side of that, you'd have X's, and on the left side of the loop, you'd have dots. And the way we get those magnetic field lines is because we're picturing with that current running up the wire, that would increase X's going into the loop and then dots coming on the outside of the loop. So to reinforce those X's, moving current in this way is going to start to build back up X field inside of this, and we'll get back to where we were. Again, the whole idea is that the act of doing this, it's trying to reduce it. We don't really get to a point of finally canceling it out. As long as there's still change happening, this is going to keep going on, but the goal is to try to get back to where it was. And so it's going to keep moving current until that change stops happening. Back over to our drawing. If we're running current now in this direction, it's going to flood positive charge into B, and it's going to leave A with a negative charge, and that is our voltage that's generated out of that one. So to help visualize that, there's a simulator that I'm going to put a link to that you can play around with. And in this simulator, it lets you run north and south field lines. It's about all it does, but it shows you the concept that as those field lines are intensifying, there's a direction change with how that current flows around. So you can kind of practice that hand rule just by playing around with this simulation to see how would that current roll around that coil. And you notice when you flip it to south, you kind of get this opposite effect to happen. So the link for that will be on Google Classroom as well. If you just want to play around with that to give yourself the conceptual feel and really practice how is that current moving around that wire to respond to that increase in magnetic field or decrease in magnetic field. It helps to have that visual. All right, on number 3, you got a permanent magnetic field, and I'm drawing it off to the side here, like in the orientation of the loop. And what it's not exactly clear about what this wire is. It's just like a flexible bit of wire, and so they're pulling up on it and effectively decreasing the cross-sectional area of the loop. So just imagine like a kind of a flimsy wire that you're able to manipulate at the top rather than just like a solid steel ring. So I don't know if this will come through as well as I'm thinking, but like imagine like if it was perfectly circular and you see how many field lines are inside of that. 1, 2, 3, 4, 5, 6.5 maybe X's. And if I bow that together like this, I can't really like, you basically be pulling it up and then scrunching it together. the idea is that the effective cross-sectional area is going to be getting smaller. So yeah, maybe you lift it up a little bit so you're able to handle, a few vertical. I can't like lift this drawing that I'm doing vertically, but by lifting it up, you're effectively kind of squeezing the sides together, not allowing as many B field lines in. So what this is feeling, again, from the aspect of the loop, is that the x's are decreasing in the area. It's feeling this reduction in x field because less and less x's are inside of that ring as you make it really skinny. So it's going to run current to try to counteract that. In the same way that number 3 tried to reinforce those x fields, number 2 tried to reinforce those x fields. Number 3 is going to do that as well. So if we want more x's to show up, we're going to run current. Again, it's kind of this clockwise orientation when viewed from the north pole of the magnet, because by doing that, you get x's on the inside to build up and dots on the outside. No matter which, you can try it out. No matter which side you put your hand on, if you go on the right side here and try to do your hand rule, your thumb would be pointing down. Your fingers would curl into the loop on the inside, meaning they would be X's, and they'd be coming out of the loop, out of the page on the outside. You do that down at the bottom. No matter, again, it'll always work. Your hand rule, if you use your right hand, move your thumb in the direction of the current, and your X's will be on the inside of the loop, your dots will be on the outside, no matter which orientation. All right, so I'm just going to conceptually talk about 4, 5, and 6 instead of going through the entire thing. And number 4, just pay attention to think about if this is all in the same plane, are there any real field lines traveling through your loop? Or in the sense that if you move it back and forth, if you're on the same plane as this stuff, there's really no orientation of your area that's 90 degrees to those B field lines. So that's on number 4. It's kind of a more conceptual problem. Number 5, so again, the permanent magnet would stay in place here, but you're going to start rotating the loop. So I still want you to follow the ideas that if it senses a field weakening, whether that be positive or negative, whether it be like field lines into the loop or out of the loop, whichever it's sensing is reducing, it's going to try to work to boost that back up. Or if it senses something increasing by the fact of it rotating, it's going to try to lessen that effect. So it's always trying to do the opposite of what's happening to the field. It's going to create field lines that would restore back to the original conditions. Number 6, same way, we're just looking at it in a little bit different orientation. So the rotation happening, it's actually starting like number 4, but then it's going to rotate towards that south pole of the magnet. So keep in mind on the south pole of the magnet, in the picture that's over here, for the south pole, the field lines come in towards the south pole, and that's going to it's going to matter as far as like how you're drawing these lines into the loop as far as which is actually increasing. So it takes a little visual manipulation, but you can maybe use that link to the simulator and then just finish out 4, 5, and 6. I'd like you to leave the graphs for Monday. We're going to talk more about those voltage graphs and the sign of them. We have to do some slope work and discuss more of the equation when we get back on Monday. So that's it. Hope this helps. See you Monday.